Hello dear students. So today we are going to study a Wheatstone network. So if you remember in the previous class we had studied two important laws, that is Kirchhoff's current law and Kirchhoff's voltage law. If you remember Kirchhoff's current law, it states that the current entering the node is equal to the current leaving the node. That is algebraic sum of the current and nodes, it will be 0. And one more law, which is Kirchhoff's voltage law, what it states, the algebraic sum of the IR products is equal to the algebraic sum of the EMF present in the various branches of the circuit. Okay, so Wheatstone network is totally based on those two laws, and we are going to actually apply those laws in a Wheatstone network. So if I talk about the Wheatstone network, it's a device consisting of 4 resistance. Okay, and we are going to find the value of one resistance in terms of the other 3 resistance. So if I write Wheatstone network is a device consisting of 4 resistance. So it's a device consisting of 4 resistance, and it is used to find the value of unknown resistance in terms of 3 known resistance. Okay, so what is Wheatstone network? It's a device, it's an electrical device consisting of 4 resistance, out of which 3 resistance value we know, and it will help me to find the value of unknown resistance in terms of 3 resistance. So now we can, suppose if I have 4 resistance and out of which I know the value of only 3 resistance. So with the help of Wheatstone network, I can do certain sort of experiment which we will study in the next class, that is meter bridge and potentiometer. That will help me to know the value of this unknown resistance, that is 4th unknown resistance. Okay, now we can find the value of unknown resistance by using the balancing condition of Wheatstone network. So now we can find the value of this unknown resistance in terms of 3 known resistors by balance condition of Wheatstone network. So what if I tell you in short what is balance condition? We are going to take 4 unknown resistance, considering we know the value of the 3 resistance, and our aim is to find the value of the 4th unknown resistance. We are going to take a galvanometer as a mediator. Okay, and we are going to do certain sort of experiment, and we are going to see the deflection in the galvanometer at one particular deflection. When I connect all those resistance in one particular order at one particular length in a meter bridge, that will study in the next class, you will see that galvanometer has come to the 0. It will point towards the 0, and whenever the galvanometer points towards the 0, it is known as the balance condition of the Wheatstone network. So balance condition it will satisfy once I get this equation, R1 by R2 equals to R3 by R4. So today our aim will be to derive this formula. So in exam they will ask you what is Wheatstone network and derive the expression for balance condition of Wheatstone network, which is this formula, R1 by R2 equals to R3 and R4, where these all are 4 resistance and we don't know the value of any one of the resistance. If I know the value of any 3 resistance, I can easily do basic mathematics and get the value of unknown resistance. So the derivation will be of 5 marks. They may ask you definition and derive an expression for balance condition of Wheatstone network. Okay, so we'll start derivation. So before you do any derivation, make sure you draw the relevant circuit diagram. So the question will be asked this way: expression for balance condition of Wheatstone network. Wheatstone network is again a complex type of electrical network where I have 4 resistors, out of which I don't know the value of one resistance and I know the value of the 3 resistance. Now, expression for the balance condition of Wheatstone network. So suppose first I'll draw a diagram. Okay, suppose I have one battery which is carrying current in this direction, and suppose I have, this is my Wheatstone network. So see, how do I draw a Wheatstone network? Okay, now students, look carefully here. This is a typical diagram of Wheatstone network. Now this battery which is carrying current I, or maybe a cell, you can consider this as cell. This is node A. This will have current I1, R1. This will have I2, R2, I2, R2, and here look at the arrow mark, and here in the middle I have a galvanometer which is carrying current Ig, having resistance capital G. Okay, and this will be I4, R4, and this will be I3, R3. Point B, point C, and point D, which is the node. So you are expected to draw this neat, clear diagram. Okay, so this is the typical diagram of the Wheatstone network. I have drawn this side a little bit more. You can, with the help of scale, you can draw it neatly. Fine. Now, see here, it's a typical Wheatstone network consisting of 4 resistors: R1, R2, R3, and R4. Now here it is carrying current I1, I2, I3, and I4. Since it's a parallel connection, you should know ki current changes whereas potential difference remains same. Now please look here. The current comes I from here, and this is the common point where the current splits into 2 points, because this is a node or a junction. And node is, in what will happen in node, the algebraic sum of the current entering the node, it will be 0. Why? Because current entering the node will be equal to current leaving the node. So please focus on these arrow marks. Okay, so see here current I is coming and it is splitting into I1 and I2, I1 and I2. Look here, so I'll draw this arrow mark. Please look at the arrow mark here. Okay, so from I2 it is again splitting into I4 in this way, and here the current through the galvanometer, I4 and I3. Look here. So I1, then it splits into Ig and I3, and at this point I4 and I2. So please look at the arrow marks, because these arrow marks helps me to know the direction of the current, and once I know the conventional directions of the current, I can take them positive and negative, as in the case we have seen in the Kirchhoff's current law, that current entering the node should be equal to the current leaving the node. So please draw a neat diagram and make sure ki where you are drawing the arrow marks, because arrow mark will give me the direction of the current. So if I take a conventional direction, this is positive, this is negative. So if I go upwards, the current is coming downwards, so I'll take negative this part. Okay, here again positive, and in this direction I may take negative. So follow one proper sign convention. Okay, fine. So I'll erase this. I want you to remember this diagram while deriving it. Okay, I hope you are drawn into your books. So let's erase this also. So for my reference, I will just draw a simple diagram here, so that it will help me to derive it very easily. So a small diagram here. Here I1, R1, here Ig, here I2, R2, here I4, R4, here I3 and R3. So this is point node A, node B, node C, and node D. Okay, so now one thing, using KCL at point A, using KCL at point A. Now we are going to apply Kirchhoff's current law at node A. So in Kirchhoff's current law, we have told ki current entering the node is equal to current leaving the node. So for your reference, or if you have seen in the previous diagram, at A current I is entering. At A current I is entering. So see here, from here current I is entering, and at this point it gets splitted up, I1 and I2. So if I apply KCL, Kirchhoff's current law, at node A, so current entering the node is equal to current leaving the node. Let this be equation number 1. So current entering the node will be equal to current leaving the node. So what has entered at node A? I. And what it has left? I1 and I2. Similarly, KCL, applying KCL at node B. Now please look carefully at B. At B, current I1 is entering, and this I1 is again splitting into IG and I3. IG and I3. Where? So here current I1 is entering. Please look into the previous diagram if this is not visible to you. Okay, this is just for my reference so that it will be very easy to derive the things. So here I1 is entering, and how it is left? IG plus I3. Give this as equation number 2. So again I have applied Kirchhoff's current law. You know, current entering the node is equal to current leaving the node. Similarly, apply KCL at node D. Now look here, at node D, at this point. So at this point, I2 is also entering and IG is also entering, where IG is the current through the galvanometer. At the center, I have galvanometer. The galvanometer is the person who is going to show the balance condition once it points towards the 0. Okay, so at D, I2 is also entering and IG is also entering. And if you see carefully, this entered current is going towards I4 and I4. Okay, so at D, what is happening here is I2 plus IG is equal to I4. So this is Kirchhoff's current law at node D. Simple. Current entering is equal to current leaving the node. Okay. Now I am going to apply Kirchhoff's voltage law at mesh AB DA. So now again I will apply Kirchhoff. So this is Kirchhoff's current law. Here I have simply applied KCL law. Now I am going to apply Kirchhoff's voltage law. So for Kirchhoff's voltage law, I told you that it should be a closed path. An electrical network should be of closed path. So my closed path or a mesh, I told you it is also known as mesh. So mesh here is ABDA. And I had told you that some of the IR products will be equal to the 0. Net potential of the system will be equal to 0. I told you this thing. So now apply Kirchhoff's voltage law at mesh ABDA. Look here, can I write I1 R1 plus IG G, where G is the resistance of the galvanometer, IG is the current through the galvanometer, minus I2 R2. This will be equal to 0. This is Kirchhoff's voltage law at mesh ABDA. You might be wondering why I have taken negative here. See here, it's a loop in this direction, ABDA. So here you can see current is entering in this direction, but when I want to go to this path, the arrow mark is pointing opposite to me. So I will take a negative sign here. Is that clear? Similarly, applying KVL at mesh BCDB. Now applying KVL at mesh BCDB. Now see here, BCDB. So now again apply here. It will be what? I3 R3 minus I4 R4 minus IG G equals to 0. I'll give this equation 4 and this as equation 5. Now again look carefully here. This is my mesh BCDB. So apply current is in this direction, I3 R3, and my mesh is here, CD. But the arrow mark, the current is in opposite direction, so I'll take I4 R4 as minus I4 R4, and my mesh completes in this direction. But in this direction, you can see that this mesh BD is in opposite direction, so I'll take IGG. IG is the current in the galvanometer, and G is the capital G is the resistance of the galvanometer. Yes. Okay. So this is what applying KVL law. So just understand Kirchhoff's current law and Kirchhoff's voltage law and simply apply them to this complex electrical network consisting of four resistors, out of which three are known and one is unknown. Now, as I told you, we are going to find the balancing condition, and you already know the formula out of it. But to satisfy the balancing condition, I have told you earlier that the galvanometer reading should be 0. Once the galvanometer reading is 0, then only the balancing condition will be satisfied. So we will take let current through the galvanometer be 0. Now this condition is very important because this condition will determine the balancing condition of the galvanometer. So we will assume let the current through the galvanometer will be 0. This is theoretical assumption. But once you do the practical, we have to take care the readings in the galvanometer should be pointed towards the 0. So we will consider let current through the galvanometer will be 0. So if Ig is equal to 0, what will happen to equation 2? Look carefully here. It will become I1 is equal to I3. Just look carefully. So what will happen to equation 2? I1 will become equals to I3 because this is 0. So this will be equation number 6. Similarly, what will happen to equation 3 if Ig is 0? It will be I2 equals to I4. Yes or no? Give this as equation number 7. So what I have done, I have satisfied the balancing condition Ig equals to 0. So if Ig is equal to 0, then I1 will be equal to I3 and I2 will be equals to I4 as per this mathematical rule. Similarly, what will happen to equation 4? So I will erase this. I will erase the upper part now. Okay. Okay, I'll erase this also. So now what will happen to the equation 4? Look here carefully, please. So this will be what? I1 R1 minus I2 R2 will be equal to 0. Since Ig is equal to 0, 0 into G will be what? 0. So what I am left here with is I1 R1 minus I2 R2 equals to 0. Is that clear? So I can write it as I1 R1. I'll shift this minus this side, so it will become I2 R2 equals to 0. Is that clear? Not, I'll not write to 0 because I have shifted this side. So this will be equation number 8. Is that clear? Similarly, again I will substitute Ig equals to 0 in equation number 5. So what will be this? I3 R3 minus I4 R4. This will be equals to 0. Now since current through the galvanometer is 0, again this equation will reduce to I3 R3 minus I4 R4. This will be 0. 0 into G will be 0. This will be equal to 0. So again what I will do here is I3 R3. This will be equals to I4 R4. This will be equation number 9. Equation number 9. So I have shifted it to this point. Is that clear? Okay. Fine. Now please look carefully here. I am going to divide equation 8 by 9. So dividing equation 8 and 9, what will I get here is, look at equation 8 and look at equation 9. So this will be I1 R1 divided by I3 R3. This will be equals to I2 R2 divided by I4 R4. So simply I have divided equation 8 and 9, so that now again look carefully here. Here I1 is equal to I3. So here instead of writing I1 I can write I3, or instead of I3 I can write I1. Similarly I2 is equal to I4. So instead of writing I2 here I can also write I4, or instead of I4 I can also write I2. Look here, from this equation I1 is equal to I3. So can I write I1 R1 divided by I1 R3? Is that clear? What I am doing here is, instead of writing I3 I am writing I1, because I1 is equal to I3. Same thing I can write I2 R2 divided by I2 R2. Yes or no? So instead of writing I4, because I4 is equal to I2, I will write I2. So you can look carefully, I1 gets cancelled, and I2 also gets cancelled. So what you are left here with is, you are left here, so you are left with R1 divided by R3. This is equal to R2 divided by R4. So I can still modify this equation as R1 by R2. I bring this 2 here and I shift that 3 up here, R3 by R4. So this is the balancing condition of the Wheatstone network. So this is the balancing condition of the Wheatstone network. So most probably they may ask you this derivation for the 5 marks. Either they may ask for combination of cells in parallel, or they may ask this derivation for the 5 marks. Is that clear? Okay. So in the next class we will be studying potentiometer and meter bridge. Okay. So that will conclude your current electricity topic, which was having a weightage of 13 marks. Okay. Fine. I hope you have followed today's derivation. Most important derivation and very easy to understand. Just you should know what is Kirchhoff's current law and Kirchhoff's voltage law, and go on applying those law and solve mathematically. Is that clear? Fine. Thank you.